Good morning, everyone. Today I will explain my homework for number 1. The main task of this homework is to create the time domain model of a spring damper system first, then use the Laplace transform to get its transfer function. Let's start with the problem background. First, let's understand what this system is about. The spring damper model is a simple way to represent medical system, like the sample seen in a car. We use it to study how the system moves and responds. Now let's look at the system parts and key values. The main part here is a mass of 1 million kilometer. There's also a damper with a value of 50 nu. A damper helps slow down the mass's movement, like how a shock absorber works in a car. The input to this system is a force. This is what pushes or pulls the mass. This system is a first-order system. First-order system has a general form. Next, we will build the time domain model. To do this, we use Newton's second law. You might remember this form: physical force equals times acceleration. First, let's analyze the force acting on the mass. The input force, this is the force that drives the system. Second, the damping force. This force opposes the mass's moment. Its value is b times velocity. Velocity is how fast the mass moves, and it's also the derivative of displacement. Displacement is how far the mass moves from its starting point. By Newton's second law, the net force on the mass equals mass times acceleration. The net force here is the input force, the damping force. Acceleration is the derivative of viscosity. This is our time domain different equation. Now, why do we use the Laplace transform? Because different equations can be hard to solve. The Laplace transform converts this dynamic time-based equation into simple analyzed equation in the complex frequency domain. This makes analyze much easier. We only need a few key rules for our system. Means the mass starts from rest. First, the Laplace transform of a collocation, where V is the Laplace transform of velocity. The Laplace transform of velocity is just V. 3. If the input force is a step function, its Laplace transform Fs is 500. In simple terms, the Laplace transform takes how the system changes over time and turns it into a static relationship so we can use Pascal math to find the system behavior. Now let's use the Laplace transform to find the transfer function. The transfer function tells us how the output responds to the input in the complex frequency domain. Now let's check if the system is stable. A system is stable if all poles are in the left half of the complex plane. Size S is negative. It's in the left half of the complex plane. So our system is stable. That means if we apply a force, the mass won't keep moving faster forever. It will settle into a steady speed. Let's wrap up what we did today. First, we reviewed the key knowledge. Time domain model using Newton's second law, Laplace transform, and the transfer function. The logical way followed is a clear loop. Start with the physical spring damper system. Derive the time domain different equation. 3. Use the Laplace transform to get the transfer function in the complex frequency domain. This loop complete the process of model transformation, analyze, solve for understand how the system work. This is all my answer. Thanks for your listening. Goodbye.